Welcome. Tonight we are going to spend time with the animal that has lived in the human imagination longer than almost anything else. Not a dragon, not a sea monster from the edge of an old map. Something real, something that has been swimming in the ocean since before the first tree grew on land, since before the first flower opened toward any sun, since before anything we would recognize as a modern animal had taken its final form. We are going to the ocean, not the bright, warm ocean near the shore that tourists photograph and children splash in. We are going deeper than that and wider, into the open blue water where the surface stretches in every direction without a single landmark, without a bottom you can see, without any reference point except the light above and the dark below. We are going to where the sharks are, and we are going slowly, the way the ocean moves, in long unhurried swells that have been rolling across the surface of the water since long before anyone was here to watch them. Find your comfortable position now. Let whatever is holding you take your full weight. Let the muscles of your shoulders and your neck release whatever they have been holding. Let your jaw unclench. Let the small tensions around your eyes soften. There is nothing required of you for the next hour except to breathe and to listen. The sharks have been in the ocean for 450 million years. They were here before the Atlantic Ocean existed. They were here before the continents were in anything like their current positions. They have survived 5 mass extinctions, events that erased more than half of all life on Earth, and they came through each one and continued, in the dark water, doing what they have always done. They are not in any hurry, and tonight neither are you. The shark is perhaps the most misunderstood animal on Earth, not because it is rare or shy or difficult to observe. It is misunderstood because of the particular quality of the fear it inspires, a fear so specific and so complete that it has become its own category of dread, something closer to mythology than to natural history. We have built an entire cultural architecture around the shark, a set of images and stories and instinctive responses that tell us the shark is a monster, a mindless killing machine, the embodiment of the ocean's hostility toward everything that is not itself. And in doing so, in loading so much of our anxiety onto this single animal, we have made it almost impossible to see what the shark actually is, which is something far more interesting, far more strange and far more ancient than any monster we could invent. The first thing to understand about the shark is the number 450 million. Say it slowly and try to feel the weight of it. 450 million years. That is the approximate age of the oldest known shark fossils, fragments of scales and teeth from the Ordovician period, from a time when the most complex life on Earth was still confined almost entirely to the ocean, when the land above the shoreline was bare rock, when no animal had yet crawled out of the water and taken its first breath of air. The sharks were already there, already swimming, already doing recognizably shark-like things in the Ordovician seas, and they have been there ever since. Through the Devonian, when the first fish ventured onto land and became the ancestors of every tetrapod that ever lived. Through the Carboniferous, with its vast coal swamp forests and its enormous insects. Through the Permian extinction, the worst in Earth's history, which killed more than 90% of all species. Through the Triassic, when the first dinosaurs appeared. Through the Jurassic, when the dinosaurs ruled. Through the Cretaceous, when the asteroids struck and the world ended and began again. Through all of the Cenozoic, the age of mammals, the long unfolding of the world as we know it, from its devastated beginning to the present night, with you breathing slowly in the dark and the sharks as they have always been in the water. The sharks did not survive all of this by being simple. That is the first correction the evidence demands. They survived by being remarkably sophisticated, by developing over 450 million years of continuous evolutionary pressure, a set of sensory systems, behavioral strategies, and physiological adaptations that are, in several respects, more refined than anything possessed by the mammals that came so much later. The shark is not a leftover. It is not an evolutionary placeholder, a primitive design that has been kept around by geological inertia, while the real animals, the sophisticated ones, evolved around it. The shark is the product of 450 million years of refinement. Every structure in its body, every sense organ, every behavioral pattern has been tested against the reality of the ocean for longer than any other predator lineage on Earth. When you look at a shark, you are looking at the result of more evolutionary testing than has been applied to any other group of large animals alive today. There are more than 500 species of shark. 500. This is a number that surprises almost everyone, because when most people think of sharks, they think of 1, the great white, perhaps 2, the great white and the hammerhead, perhaps 3, adding the whale shark. But the 500 species of shark represent an extraordinary diversity of form and lifestyle and ecological role. From the whale shark, the largest fish in the ocean, which filters plankton through its enormous gape and reaches lengths of 18 meters, to the dwarf lantern shark, Etmopterus perrier, which fits in the palm of a human hand and hunts small crustaceans in the deep water off the coast of Colombia. From the great white, Carcharodon carcharias, which hunts elephant seals in the cold waters off South Africa and California, to the epaulette shark, Hemicillium ocellatum, which walks on its fins across exposed reef flats at low tide, hauling itself from pool to pool in search of trapped fish. The sharks have found a way to live in almost every marine environment on Earth, from the surface of the tropics to the floor of the deep sea, from river mouths to the open ocean, from polar waters to equatorial reefs. They are not one thing, they are 500 things, 500 different answers to the question of how to be a shark in the world. Let your breathing slow a little more now. The ocean is wide and deep and full of these 500 answers, moving through the water in the particular way that each species has refined over millions of years, and we are going to spend time with several of them tonight. Not rushing, not cataloging, simply being present with each one long enough to understand something of what it is, what it does, how it moves through the world that it has inhabited for so much longer than we have. Begin by letting the image of the surface of the ocean settle in your mind, the slight movement of it in the night wind, the way the light from the stars touches it and scatters, the vast flatness of it, extending in every direction, and beneath it, invisible from above, the shapes moving through the blue dark water, the shapes that have been moving through it since before the stars above were in their current positions. The great white shark is where we begin, because it is where the imagination always begins, and because it deserves to be met on its own terms, rather than on the terms that popular culture has assigned to it. Carcharodon carcharias. The name means jagged tooth. A male great white reaches about 4 meters in length. A female, which is larger, can reach 6 meters and weigh more than 2,000 kilograms. 2,000 kilograms. The weight of a small car, moving through the water with a propulsive efficiency that no submarine of comparable size has ever matched, generated by the lateral sweeping of a crescent-shaped tail that is among the most hydrodynamically refined structures in the natural world. The great white is warm-blooded, or more precisely, it is regionally endothermic, capable of maintaining its core body temperature and the temperature of its brain and sensory organs significantly above the temperature of the surrounding water. This is unusual in fish, and it is one of the reasons the great white can operate effectively in the cold water it prefers. A cold-bodied predator in cold water is slow. A warm-bodied predator in cold water is fast, its muscles contracting quickly, its brain processing information rapidly, its reactions close to what a mammal of comparable size can achieve. The great white hunts in a way that reflects a very specific evolutionary history in a very specific ecological context. Off the coast of South Africa, near Seal Island in False Bay, the white sharks hunt Cape Fur seals, and the hunting strategy they have developed is one of the most dramatic predation events in the ocean. The seals leave the island each morning to feed in the bay, and as they swim away from the rocky shore, they cross a channel of deeper water. In that channel, the sharks wait below. Not at depth exactly, but below the sight line of the seals at the surface, in the dim water perhaps 20 to 30 meters down, looking up. The seal at the surface, backlit by the sky, is a clear silhouette. The shark, from below, can see it perfectly. The seal, looking into the darker water below, cannot see the shark at all. The attack comes from beneath, a vertical rush of extraordinary speed, the shark accelerating from 20 meters down to the surface in less than 2 seconds, sometimes breaching completely clear of the water, carrying the seal into the air. The impact is delivered at speed that researchers have measured at up to 40 kilometers per hour. It is over before the seal has time to process that it has begun. The great white does not always kill immediately. It often delivers a single large bite and withdraws, waiting for the prey to weaken from blood loss before returning to feed. This behavior, which has contributed to the myth of the shark as a calculating, patient, malevolent intelligence, is actually simply efficient. The seal's foreflippers contain heavy bone and muscle, capable of delivering a damaging blow. A wounded shark in cold water, far from shore, faces a serious survival threat. The bite and wait strategy minimizes the risk to the predator. It is not cruelty, it is not deliberation. It is the behavioral output of a nervous system refined over millions of years of hunting in exactly these. The sensory systems that allow the great white to find that seal in the dark water below deserve attention, because they are extraordinary in a way that the shark's teeth and size tend to overshadow. The shark has 7 senses compared to the human 5. Vision, hearing, smell, taste, and touch it shares with us in modified forms adapted for the aquatic environment. The lateral line system, a network of pressure-sensitive organs running along the sides of the body, allows the shark to detect the pressure waves created by the movement of other animals through the water, a mechanical sense that has no equivalent in any terrestrial vertebrate. And the ampullae of Lorenzini, the gel-filled pores visible as small dark spots around the snout of most shark species, allow the shark to detect the electrical fields generated by the muscles and nerves of living organisms. Every living animal produces a weak bioelectric field. The shark can detect this field at close range, and in the final moments of an attack, when sediment or turbidity might obscure vision, the electrical sense guides the jaws to within millimeters of the target. The olfactory system of the shark is the sense that the mythology has latched onto most firmly. The shark can smell blood in the water at concentrations of 1 part per million. This is a fact. It is also, like most facts about the shark's senses, more nuanced than it appears. 1 part per million is detectable, but the shark does not track a smell the way a bloodhound tracks a scent trail on dry land. It detects chemical gradients in the water, swimming in the direction of increasing concentration, following the gradient toward its source. In practice, a shark can detect blood at considerable distance in favorable current conditions. Unfavorable currents, turbulence, and the diffusion of chemicals in 3-dimensional water rather than along a 2-dimensional surface mean that in many conditions, the effective detection range is much shorter than popular accounts suggest. But the fundamental capacity is real and remarkable. The shark knows the water in a chemical dimension that we cannot access, reading information from the dissolved molecules that the current carries that tells it, with extraordinary precision, what is alive in the water around it and in what direction. Let that settle for a moment. The shark is not moving through the ocean the way we move through a room, navigating primarily by sight, in a world that is largely visually defined. It is moving through a world that is also chemically defined, electrically defined, mechanically defined. It is reading the ocean the way we might read a page of text, multiple channels of information arriving simultaneously, each one contributing to a composite picture of the environment that no human sensory system could assemble. The ocean, for the shark, is not dark. It is not featureless. It is richly, continuously, overwhelmingly informative. And the shark's nervous system, refined over 450 million years to extract meaning from all of that information, is processing it constantly, orienting the animal in its world with a precision and a completeness that the animal's reputation as a mindless primitive does not begin to capture. The hammerhead sharks are perhaps the clearest illustration of the principle that the shark's form follows function in ways that evolution has pushed to extraordinary extremes. The cephalofoil, the flattened, laterally extended head that gives the hammerhead its name, is one of the most distinctive structures in the ocean, and for most of the 20th century, its function was debated without resolution. It looks strange enough that the explanations proposed for it ranged from the plausible to the fanciful. It might improve hydrodynamic performance. It might function as a bow plane like the diving planes on a submarine, giving the shark greater maneuverability. Both of these may be partially true, but the most important function of the cephalofoil appears to be sensory. The ampullae of Lorenzini, The electroreceptive organs distributed across the snout and the underside of the head in other shark species are distributed across the entire ventral surface of the cephalofoil in the hammerhead. The wider the head, the larger the area over which these electroreceptors are distributed, and the greater the spatial resolution of the electrical map the shark creates of the seafloor below it. The great hammerhead, Sphyrna mocarin, sweeps its wide head back and forth across the sandy seafloor like a metal detector, scanning for the bioelectric signatures of stingrays buried in the sand. The shape of its head is the shape of its primary hunting instrument, and the hunting instrument is a sense organ of extraordinary precision. The great hammerhead is one of the most impressive predators in the ocean, reaching lengths of 6 meters and demonstrating hunting behaviors that require a level of sensory integration and behavioral flexibility that the word instinct does not adequately describe. In studies of hammerhead predation on stingrays, researchers have documented sharks using the leading edge of the cephalofoil to pin a stingray to the seafloor before pivoting to bite, a behavior that requires precise coordination between the sensory input from the electroreceptors, the physical pressure on the cephalofoil, and the positioning of the jaws, which are located well behind the leading edge of the head. The shark has to calculate, in real time, the relationship between where it is sensing the prey and where its jaws are, and adjust its body position accordingly. This is not simple. It requires spatial reasoning, and the hammerhead's brain, which is proportionally larger relative to body size than the brains of most other shark species, appears capable of providing it. The whale shark, Rhincodon typus, is the largest fish in the ocean, and it is as far from the great white in its biology and its ecological role as it is possible to be while remaining within the same class of animals. The whale shark is a filter feeder. It opens its enormous mouth, which can reach a width of more than 1.5 meters, and it swims slowly through concentrations of plankton, small fish and fish eggs, allowing the water to pass through its gills and filtering out the organisms on specialized structures called filter pads. A whale shark consumes tons of plankton and small fish per day, doing so at a leisurely pace that reflects its ecological position as a primary or secondary consumer rather than an apex predator. It is, by temperament and by design, completely unaggressive toward anything it cannot filter. Divers swim alongside whale sharks with no more risk than they would swim alongside a very large, very slow-moving whale. The whale shark is aware of the divers. Its large eyes, positioned on either side of its wide flat head, track them. It adjusts its position occasionally to avoid contact, and then it continues on, filtering the water, doing what it has been doing for millions of years, entirely indifferent to the observers. The whale shark's migration patterns connect oceanic regions that would otherwise seem unrelated. Individuals tagged off the coast of the Yucatan Peninsula have been tracked crossing the Atlantic to West Africa. Sharks that aggregate seasonally in the waters of Western Australia to feed on the mass spawning of coral and fish eggs follow routes through the Indian Ocean that researchers are still mapping. The whale shark is not a resident of any particular place. It is a citizen of the open ocean, following the blooms of productivity that move with the seasons and the currents, traveling distances of thousands of kilometers per year in the slow, unhurried way of an animal that has no predators, no territorial rivals, and no energetic constraints that require it to hurry. It simply moves through the blue water, all 18 meters of it, filtering the abundance of the sea, and the ocean moves around it. The blue shark, Prionace glauca, is perhaps the most successful large shark in terms of global distribution, found in every ocean from the tropics to the edges of the polar seas. A slender, indigo blue animal with extraordinarily long pectoral fins and eyes that are large and dark and give it the quality in underwater photographs of looking directly at the camera with something that resembles curiosity. The blue shark is an open ocean species, a pelagic wanderer that spends its life in the vast, largely featureless expanse of blue water, far from any coast. It follows the same large-scale current systems that the whale shark follows, but for different reasons. The blue shark follows its prey, primarily squid and small fish, which aggregate along the boundaries of current systems at the edges of upwellings, in the zones of mixing where different water masses meet and plankton blooms, and the food chain above it flourishes. The blue shark has one of the longest migrations of any shark species, with tagged individuals tracked crossing the Atlantic multiple times. A blue shark tagged off the coast of New York has been recaptured in the waters near Brazil. A shark tagged off Portugal has been found in the Caribbean. The blue ocean is not a barrier to them. It is a highway. They move through it with an efficiency that reflects a body plan optimized for sustained open water cruising, the long pectoral fins providing lift, the streamlined body minimizing drag, the heterocircled tail providing forward thrust with the slow, powerful sweeps that can be maintained indefinitely without exhaustion. The blue shark does not sprint, it cruises, and in cruising, it covers the ocean. Let your breathing slow again. We are in the open water now, far from any shore. The water blue above and dark below, and in every direction nothing but more water. This is the world the blue shark lives in. This is the world that most of the ocean's sharks inhabit, not the coastal shallows that humans encounter in beach warnings and news reports, but the vast open pelagic zone, the largest habitat on Earth, where the water is deep and the nearest land is hundreds of kilometers away in any direction. Most shark encounters with humans happen in a thin strip of coastal water, the border zone between the shark's world and ours. What happens in the open ocean, in the blue water far from any shore, is almost never seen and is almost never what we imagine. The oceanic white-tip shark, Carchahinus longimanus, is one of the open ocean species that has contributed most to the shark's reputation for danger, not through recreational diving encounters or beach incidents, but through its behavior in the specific and horrifying circumstances of shipwrecks and plane crashes in warm ocean water. The oceanic white-tip is a large, thick-set shark of the open pelagic zone, typically reaching 2 to 3 meters in length, with distinctive rounded white-tipped fins that make it unmistakable in the water. Jacques Cousteau, who encountered it often during his decades of ocean exploration, called it the most dangerous of all sharks, not because it attacked divers under normal circumstances, but because of its behavior around injured survivors in the water after maritime disasters. The oceanic white-tip is a scavenger as much as a predator, and it is attracted powerfully and persistently to disturbances in the water, to the sounds and chemical signals of struggling or injured animals. In the open ocean, where food is unpredictable and often scarce, this persistence is an adaptive advantage. An animal that investigates every disturbance and commits to any available food source will survive better over evolutionary time than one that is easily discouraged. In the context of a shipwreck, with survivors in the water producing exactly the sounds and chemical signals that trigger investigation and feeding, this persistence becomes something that is genuinely terrifying to witness and experience. The oceanic white-tip does not attack because it has identified humans as prey. It investigates because it is designed to investigate anything unusual in its environment, and it escalates from investigation to contact to biting, because contact and biting are how it gathers information about potential food sources. The fact that humans are not part of its evolved prey image does not override the investigation instinct. And in the open ocean, far from any help, the investigation of a large, persistent, determined shark is something that no amount of understanding makes easier to endure. The tiger shark, Galiocerdo cuvier, is the species that most complicates any attempt to categorize sharks into the dangerous and the harmless, the aggressive and the passive, the threat and the non-threat. The tiger shark is large, reaching 5 meters and more than 600 kilograms in adults. It is found in warm coastal and offshore waters across the tropics and subtropics, and it is a dietary generalist of an extreme kind, consuming sea turtles, dolphins, seabirds, stingrays, other sharks, fish of all kinds, jellyfish, carrion, and, in what is perhaps the most striking testament to its catholic appetite, an extraordinary variety of non-biological material. Researchers examining tiger shark stomachs have found license plates, rubber tires, the intact bodies of chickens, unopened cans of food, pieces of clothing, a full suit of armor, and a drum. The tiger shark does not discriminate. It investigates, it bites, And if what it has bitten appears to be something that could provide nutrition, it consumes it. This approach to feeding makes it genuinely more dangerous to humans than most shark species, because a shark that bites first and evaluates later, rather than evaluating and then biting only identifiable prey, creates a different kind of risk profile for swimmers and divers who enter its range. And yet the tiger shark is also, like all sharks, not a creature of malice. It is a creature of appetite and investigation, operating according to the logic of its evolutionary history in an environment where food is unpredictable and where anything unfamiliar in the water might be food. The human swimmer at the surface of a warm tropical ocean, viewed from below, is an unfamiliar shape. The splashing of hands and feet creates pressure waves. The sunscreen and the sweat and the trace elements of the body create a chemical signature. All of this is information to the tiger shark, information that triggers investigation, and investigation sometimes leads to contact. The shark that bites a human being is not attacking an enemy. It is gathering information about a potential food source in the only way its biology has provided for gathering that information. The fact that it is incorrect about the food source does not change the mechanism, and the human being on the receiving end of that information-gathering process experiences something that has nothing to do with being misidentified. The bull shark, Carcharinus leucus, is the shark that has contributed most to human fatalities worldwide, and the reason is its combination of large size, aggressive feeding behavior, and extraordinary tolerance for fresh water. Most sharks are obligate marine animals. Their physiology is tuned to salt water, and they cannot survive in fresh water for more than very short periods. The bull shark is different. Its kidneys are capable of osmoregulating across a remarkable range of salinity, allowing it to move freely between saltwater, brackish estuaries, and fully fresh river water. Bull sharks have been found in the Amazon River more than 4,000 kilometers from the ocean. They have been documented in the Mississippi River, in the Brisbane River flowing through the center of Brisbane, in Lake Nicaragua, a freshwater lake in Central America, connected to the Pacific by a river that the bull sharks have been ascending for so long that they were once considered a distinct landlocked species. They are in the Zambezi River in Africa, and the Ganges in India, and the rivers of Southeast Asia, and in countless coastal estuaries around the world. This freshwater tolerance places the bull shark in environments that no other large shark occupies, and those environments are the ones where humans concentrate. Coastal cities are built on rivers and estuaries. People swim and fish and wash in those rivers and estuaries, and the bull shark, moving freely between the open ocean and the river, follows the food and encounters the humans in numbers that no other species of comparable size does. The bull shark attacks are overwhelmingly in shallow water, often in turbid conditions, often near beaches or river mouths where visibility is poor, and where the shark is navigating partly by pressure detection and electroreception rather than vision. It does not see a human swimmer clearly. It detects a disturbance in the water. It investigates, and sometimes the investigation escalates. Let your body feel heavy now, the way water makes heavy things feel lighter, the way the ocean supports everything that floats in it without effort, without complaint, without any awareness of what it is holding. The sharks are in the water right now, as they have been for 450 million years. The bull shark is in some river, or estuary, or coastal bay, moving through water that is slightly brackish, navigating by the senses that evolution has given it, looking for food in the way it has always looked for food. The tiger shark is somewhere in the warm tropical water, its wide eyes reading the ocean around it, its nostrils passing the chemistry of the current. The oceanic whitetip is in the open blue, its white-tipped fins cutting through water that is deep beneath it in every direction. The great hammerhead is over a sandy flat, sweeping its extraordinary head back and forth, reading the electrical signatures in the sand. The whale shark is filtering the water somewhere in the open ocean, indifferent to the scale of what it is, the largest fish in the sea going about its enormous, gentle business. The shark's relationship with time is something worth sitting with. 450 million years is not simply a long time. It is a duration that encompasses almost all of the history of complex animal life on this planet. The shark evolved before the first forests existed, before the first seed plant, before any vertebrate had walked on land. It has been in the ocean through every transformation of the physical world, through the opening and closing of ocean basins, through the rise and fall of sea levels by hundreds of meters, through ice ages that covered a third of the planet's surface in glaciers, through warm periods when palm trees grew at the poles. The shark's body plan, the cartilaginous skeleton, the heterocercal tail, the placoid scales, the multiple rows of teeth that replace themselves continuously throughout the animal's life, has proven so functional across so many different ocean conditions that it has not required fundamental revision in 450 million years. This is not stasis. The sharks of today are not the same as the sharks of the Devonian. They have evolved continuously through the normal processes of natural selection and speciation. But the fundamental architecture of what a shark is has remained stable because the fundamental architecture works. The ocean is old, and the shark fits the ocean, and neither has needed the other to change. The deep-sea sharks are the least known and in some ways the most remarkable because they have extended the shark's already extraordinary range of habitat into environments that the cartilaginous fish lineage was not obviously designed for. The Greenland shark, Somniosus microcephalus, lives in the cold, deep water of the North Atlantic and Arctic Ocean, diving to depths of more than 2,000 meters, and it grows slowly, almost imperceptibly slowly, adding less than a centimeter in length per year. A Greenland shark that is 5 meters long is very old. Radiocarbon dating of the proteins in the eye lenses of large Greenland sharks, tissues that are laid down in layers from birth and are not replaced, has revealed ages that are extraordinary, even by the standards of long-lived animals. The oldest individual in one study was estimated at 392 years old, with an uncertainty range that extended past 500 years. The Greenland shark that is alive in the cold water of the Arctic right now may have been born before the first European colonists arrived on the coast of North America. It was alive during the American Revolution. It has been in the ocean for the entire history of industrial civilization. It will likely still be in the ocean after everyone reading this is gone. The Greenland shark moves through the dark cold water of the deep Arctic at about 1 kilometer per hour, the slowest swimming speed of any shark species. Its metabolism is correspondingly glacial. It feeds on fish, seals, and carrion, and the infrequency of its meals is consistent with a metabolic rate so low that the animal requires very little energy to sustain itself. In the cold, dark water it inhabits, this is an advantage. The deep Arctic does not offer the warm productivity of the tropical reef or the open pelagic zone. It offers cold and pressure and the slow drift of organic material from the layers above. The Greenland shark has tuned its biology to that environment with the same thoroughness that every shark species has tuned its biology to its own particular world. The frilled shark, Chlamydocoelicus anguineus, is so different from what we think a shark is that its discovery by Western science in the 19th century was met with genuine confusion about its classification. It is long, sinuous, eel-like in form, with 6 pairs of gill slits fringed with ruffled edges, a head that looks nothing like a typical shark, and teeth shaped like tridents, each one bearing 3 sharp, backward-pointing cusps, arranged in 25 rows around the jaw. It lives in the deep ocean, at depths of up to 1,500 meters, and it is almost never seen alive. The specimens that have reached the surface have all been very close to death, unable to survive the decompression and the warmth of surface water. What we know about how it lives has been inferred from the anatomy rather than observed directly. Its jaws appear capable of enormous gape, suggesting that it captures prey by engulfing rather than by biting. Its backward-pointing teeth would prevent prey from escaping once seized. Its flexible, sinuous body would allow it to maneuver in the complex, 3-dimensional space of the open, deep ocean in ways that a more rigid shark could not. The frilled shark is a shark that looks, in almost every respect, like something that evolution designed specifically for the deep, for the dark, for the cold, for the particular challenges of an environment that the earliest sharks would not have recognized. The cookie-cutter shark, Icystius brasiliensis, is small, rarely exceeding 50 centimeters in length, and it is one of the most ecologically remarkable predators in the ocean. It does not kill its prey outright. It takes bites from much larger animals, Dolphins, whales, large tuna, swordfish, even the occasional great white shark. All carry the distinctive circular scars of cookie-cutter shark bites. The shark uses its large lower teeth to cut a circular plug of flesh from the body of its host, then twists its body to complete the excision. The bite is not fatal to the host, but it is deep and damaging, a wound several centimeters across and several centimeters deep, and it heals into a circular scar that marine biologists have used to study the movements of the cookie-cutter's victims by tracking the scars on large pelagic animals. The cookie cutter is also bioluminescent, producing a counter-illuminating glow on its underside that helps it blend with the faint light from above, and it may use this glow to attract larger animals before biting them, functioning simultaneously as camouflage and as lure in a strategy of remarkable efficiency for an animal of its size. Let your breathing slow now to the long, patient rhythm of the deep water. We are in the ocean in the dark. The sharks are moving around us in the way they have always moved. And the world is very large and very old and very full of things that have been here longer than we have, and that understand their world in ways that we are still learning the names for. The whale shark is somewhere out there in the blue water, its enormous gentle body filtering the sea. The Greenland shark is somewhere in the cold dark of the Arctic, moving at its single kilometer per hour through water that has been cold for as long as the Greenland shark has been alive, which is to say for a very long time. The great white is somewhere off a rocky coast, its water warm-cored body holding its temperature above the cold sea, its sensory systems reading the environment in 7 simultaneous channels. The hammerhead is sweeping its wide head above the sandy flat, reading the electrical signatures of the animals hiding below. The frilled shark is at depth, in the cold and the pressure, drifting through the midnight zone with its trident teeth and its ancient lineage, a creature that has been in the deep since before most of the shark species that share the ocean with it came to exist. The shark's cartilaginous skeleton is worth a moment of attention, because it is one of the features of shark biology that is most often cited as evidence of primitiveness. Most fish have bony skeletons. The shark has cartilage. Cartilage is the substance your ears and the tip of your nose are made of, lighter and more flexible than bone. The assumption has been that the bony skeleton of most fish represents an evolutionary advance over the cartilaginous skeleton of the shark. That bone came later and was better, and that the shark's retention of cartilage is a sign of evolutionary stasis. This assumption is probably wrong. The fossil record is increasingly being read to suggest that cartilaginous skeletons are not primitive, but are in fact derived, that the common ancestor of sharks and bony fish may have had a more extensively calcified skeleton than modern sharks do, and that the shark's cartilaginous skeleton represents an evolutionary response, a reduction in skeletal calcification that reduces weight, increases flexibility, and may offer advantages in the high-pressure deep-sea environments that several shark species inhabit. The shark's cartilage is not a failure to evolve bone. It is an evolved departure from bone in the direction of something lighter, more flexible, and in several respects more functional for the specific demands of an aquatic predator's life. The teeth of the shark are one of the most striking features of its biology, and they are remarkable for reasons that go beyond their sharpness. A shark does not have a fixed set of teeth that must last a lifetime. It has a conveyor belt of teeth. Behind each functional tooth in the jaw is a row of replacement teeth, progressively smaller as they extend toward the back of the jaw, each one waiting to move forward as the tooth in front of it is shed. Sharks shed and replace teeth continuously throughout their lives, with replacement cycles that vary by species from a few days to several weeks. A large shark may produce tens of thousands of teeth in a lifetime, and this continuous replacement means that the shark never has a worn or damaged tooth in functional position for long. Every bite is delivered with a fresh, sharp tooth. The edge of the tooth is never blunted by extended use before it is replaced by another. The shark's dentition is a self-renewing cutting system, perpetually maintained, never degraded by the normal wear that affects the teeth of animals that grow them once and depend on them indefinitely. The quality of the shark's skin is another feature that reflects the depth of evolutionary refinement in this lineage. The skin is covered in dermal denticles, sometimes called placoid scales, though they are more similar to teeth than to the scales of bony fish. Each denticle is a small, tooth-like structure with a pulp cavity, a dentine layer, and an enamel-like outer surface, oriented so that the tip of the denticle points toward the tail. Running your hand from head to tail along a shark's skin, you encounter little resistance. Running it from tail to head, it feels like fine sandpaper. This texture is not incidental. The denticles reduce turbulence in the water flowing over the shark's body, decreasing drag and increasing swimming efficiency in a way that aerospace engineers have studied and attempted to replicate in the design of aircraft surfaces and competitive swimwear. The shark's skin is a hydrodynamic surface that 450 million years of swimming in moving water has refined to a precision that human engineering has not yet matched. There is a quality to the shark's presence in the ocean that is difficult to describe without resorting to the language of mythology, and the difficulty is worth acknowledging because it points to something real about the animal. When a large shark moves through clear water, visible from above or alongside, there is something in the quality of its movement that is different from the movement of other large animals. It is not just the efficiency of it, though the efficiency is apparent. It is the completeness of it. The shark moving through the water is not a body in an environment. It is a body that is its environment, that fits the water so perfectly that the two seem to be a single thing. The shark's movement and the water's movement indistinguishable from each other at close range. The water flows around it the way the shark's 450 million years of evolution have shaped the water to flow, and the shark moves through the water the way the water's 450 million years of pressure on the shark's lineage have shaped the shark to move. They are not separate. They are a system. Let your body feel that quality now. The way the surface you are lying on supports you without effort, without negotiation, without any adjustment required. The way the air moves around you and through you without resistance. The way the sounds of the room settle into the background, and the body settles into the surface, and the surface supports the body, and the whole arrangement is perfectly, quietly, completely comfortable. This is what the shark has found in the water. The perfect fit between a body and its environment, achieved over a duration of time that no other predator lineage on Earth can match. The shark's brain is the next correction that the evidence demands. The traditional account describes the shark as having a brain that is almost entirely devoted to smell, a primitive stimulus response machine with no capacity for learning, memory, or anything that might be called cognitive flexibility. This account is wrong. The shark's brain is proportionally larger, relative to body size, than the brains of many mammals, including some primates. Different species of shark have brains with dramatically different proportions of the major regions, reflecting different emphases in sensory processing and behavioral complexity, just as the brains of different mammal species reflect the different demands of different ecological niches. Hammerheads have proportionally large forebrains relative to other sharks, consistent with the spatial processing demands of their complex electrosensory hunting strategy. The great white has a large olfactory region, consistent with its reliance on chemical detection across large distances. The gray reef shark has brain proportions that suggest a high degree of social complexity, consistent with the observed formation of dominance hierarchies and social groupings in this species. Sharks learn. This has been demonstrated in controlled experimental settings. Sharks can be trained to associate arbitrary stimuli with food rewards, and they remember the association across periods of weeks. They show habituation, the decrease in response to a stimulus that is repeatedly presented without consequence, which means that they are comparing current experience to stored past experience and adjusting their behavior accordingly. They show spatial learning, the ability to remember the locations of resources in their environment and to navigate efficiently between them. They show social learning in some species, modifying their behavior in response to observing the behavior of other individuals. These are not the capacities of a stimulus response machine. They are the capacities of an animal with a working memory, with the ability to learn from experience, and with the cognitive flexibility to adjust its behavior based on what it has learned. The shark is also in several species a social animal. The gray reef shark forms loose aggregations that are structured by dominance, with larger individuals having priority access to resources and smaller individuals deferring to them in encounters over food. The hammerhead aggregates in schools of hundreds of individuals at specific locations during specific seasons, a behavior whose function is not fully understood, but that is clearly more complex than the solitary hunting behavior that the shark's reputation would predict. The lemon shark forms long-term associations with specific other individuals, recognizing familiar conspecifics and treating them differently from strangers, a capacity that implies both memory and individual recognition. None of this makes the shark a social animal in the way that dolphins or wolves are social animals, but it means that the simple picture of the shark as a solitary, non-cognitive predator is not a picture that the evidence supports. Conditions. There is a word that is sometimes used to describe the quality of the shark's presence in the ocean, a word borrowed from the ecological literature that was not invented for the shark, but that fits it unusually well. The word is apex. An apex predator is one that occupies the top of the food chain in its ecosystem, that has no natural predators of its own, and that exerts a controlling influence on the ecosystem below it by regulating the populations of the animals it hunts. The shark is the apex predator of most marine ecosystems it inhabits. But the word apex, with its spatial metaphor of height and summit, does not quite capture what that means in the context of an animal that has been in the ocean for 450 million years. The shark is not at the top of the food chain in the sense of being the final achievement of the food chain, the pinnacle of evolutionary progress. It is at the top in the sense of being the animal that every other animal in its ecosystem is shaped by. The fish in the reef swim the way they swim partly because of the shark. The seal population of False Bay is the size it is and is distributed the way it is partly because of the great white. The total populations of tropical oceans are the size they are partly because of the tiger shark. The shark is not just in the ecosystem. It is one of the forces that made the ecosystem what it is, one of the selection pressures that shaped every other animal in its world over the course of hundreds of millions of years of shared evolutionary history. Remove the shark from the ecosystem, and the ecosystem changes. This has been demonstrated in places where shark populations have collapsed due to overfishing. In the Northwest Atlantic, the removal of large shark species through the 20th century led to an explosion in the population of cow-nose rays, which the sharks had been controlling through predation. The cow-nose rays fed on scallops, and the scallop population, freed from the predation pressure of the rays, also exploded briefly before the scallop population collapsed under the predation pressure of the expanded ray population. The collapse of the scallop fishery in the region was traced back through this trophic cascade to the removal of the sharks. The shark was not eating the scallops. It was not directly connected to the scallops in any way that a simple food chain diagram would capture, but it was controlling, through its predation on the rays, the force that controlled the scallops. Remove the shark and the whole chain shifts. Let your mind rest on that for a moment. The ocean is a system of connections so deep and so ramified that pulling on any part of it pulls on parts that seem unrelated, that seem separated by layers of biology and ecology and space. The shark is one of the knots in that web, one of the places where many threads come together. And the threads that come together at the shark have been there for 450 million years. They are not recent connections. They are the oldest connections in the ocean ecosystem, the ones that everything else has organized itself around. The reef fish, the pelagic fish, the seals, the sea turtles, the rays, the squid, all of them carry in their bodies and their behaviors the traces of 450 million years of living in the same ocean as the shark, of being shaped by the shark's predation, of evolving in response to the shark's presence. Remove the shark, and you remove the selection pressure that shaped the other animals. You do not simply have a quieter ocean. You have an ocean whose other inhabitants no longer know quite what they were shaped to do. The situation of the sharks in the current ocean is not good. The shark populations that existed at the beginning of the 20th century were products of 450 million years of evolutionary history, operating in an ocean that had not been systematically harvested by industrial methods. The shark populations that exist at the beginning of the 21st century are what remains after a century of intensive fishing pressure that the shark's life history was not built to withstand. Sharks are slow to mature, long-lived, and produce relatively few offspring per reproductive cycle, compared to the bony fish that commercial fishing targets. A tuna can mature in a few years and produce millions of eggs per spawning. A great white shark takes roughly 26 years to reach reproductive maturity and gives birth to litters of 2 to 12 pups after a gestation period of 11 to 18 months. When fishing pressure exceeds the shark's reproductive rate, the population declines, and most populations have declined, some dramatically. Estimates of the decline in open ocean shark populations since 1970 suggest reductions of 70 to 90% in some species. The oceanic whitetip, once described by Jacques Cousteau as the most common large animal on Earth by biomass, has declined by more than 95% in the Gulf of Mexico alone. Shark finning, the practice of removing the fins from a live shark and returning the body to the ocean to die, drives a global trade in shark fin soup that has been one of the primary forces in the collapse of shark populations across the Indo-Pacific and beyond. Bycatch in longline fisheries targeting tuna and swordfish kills millions of sharks per year as incidental victims of nets and hooks set for other species. The coastal development that destroys mangrove and seagrass nursery habitat reduces the survival of juvenile sharks before they can contribute to the adult population. And the direct persecution of sharks through culling programs and bounty schemes, motivated by the fear that popular culture has so carefully constructed around the animal, has removed individuals from populations that could not sustain the loss. But the shark is still here. 450 million years is a long time to be in the ocean, and the lineage has survived things that make the current situation look modest. The Permian extinction killed more than 90% of all species. The sharks came through. The end Cretaceous extinction killed the dinosaurs and transformed the world. The sharks came through. The question of whether the current extinction event, driven not by geology or astronomy, but by one species and its industries, will prove more challenging than the previous 5 is a question that the shark's past does not answer. Past performance is not a guarantee of future results, even across 450 million years. The shark needs the ocean to be the ocean, cold water where it has evolved for cold water, warm reef water where it has evolved for warm reef water. The open pelagic where the oceanic whitetip was once the most common large animal on Earth. The deep cold dark where the Greenland shark has been growing for 300 or 500 years. If those environments remain in something like the condition that 450 million years of evolution has tuned the shark's biology to expect, the shark will remain. It has done harder things. It has survived worse. But it has never before survived a planet that is warming faster than the geological record shows any previous warming to have occurred, with ocean chemistry changing at rates that are geologically unprecedented, with the top of its food chain removed in many regions by industrial pressure, with the nursery habitats of its young replaced by coastal development. These are new conditions, and how the shark responds to new conditions it has not encountered before in 450 million years of encountering everything else is not something we can read from the fossil record. Let that be the last weight of thought before the rest descends. Not anxiety, just acknowledgement. The shark has been here for 450 million years, and it is still here, in the ocean, in the dark, in every latitude from the Arctic to the equator, in every depth from the surface to the deep sea. The great white is somewhere off a rocky coast, its warm blood keeping its brain fast in the cold water. The whale shark is somewhere in the open ocean, its enormous body filtering the sea. The Greenland shark is in the cold Arctic dark, moving at 1 kilometer per hour through water it has been in for hundreds of years. The hammerhead is reading the electrical signatures in the sand. The blue shark is crossing an ocean on its long pectoral fins. The cookie cutter is in the twilight zone, its counter-illuminating belly glowing in the dark. The frilled shark is at depth with its trident teeth and its ancient form. All of them are in the water right now, doing what they have always done, what 450 million years of evolution has shaped them to do, in the ocean that they helped to make what it is. The ocean is very large and very old and very full, and the sharks are in it as they have always been in it, as they will likely continue to be in it long after this particular night has ended and the surface world has gone about its ordinary business. The water is dark below the surface in every place where the water is deep, and in the dark, the shapes are moving, long and patient and shaped by more time than we can hold in our minds, moving through the medium they were built for, reading the world in 7 senses simultaneously, belonging to the ocean in a way that 450 million years of belonging produces. Let your body be heavy now. Let the surface hold you the way the ocean holds the shark, without any effort required, without any negotiation, simply by being what it is. Your breathing is slow. The sounds around you are quiet or becoming quieter. The thoughts are slowing to the pace of the deep current, which is very slow, which is the pace of something that has been moving in the same direction for longer than anything on the surface has existed. The sharks are in the water. The water is in the ocean. The ocean is where it has always been, and everything is very old and very still, and moving at exactly the pace it needs to move at, in the dark, in the deep, in the patient world beneath the surface of things. Sleep now. The sharks are keeping their ancient watch. The ocean holds them as it has always held them. Everything is where it is, doing what it does in the dark and the cold and the blue and the deep. Sleep. The salmon shark, Lamna ditropis, is the great white's closest relative in the North Pacific, and it is one of the best examples of what regional endothermy allows a shark to do in cold water. Like the great white, the salmon shark maintains its body temperature significantly above the surrounding seawater, sometimes by as much as 20 degrees Celsius above the ambient temperature. In the cold, often near freezing water of the Gulf of Alaska, where the salmon shark is most commonly found, this thermal advantage is decisive. The salmon that the shark hunts are fast, powerful fish capable of impressive bursts of speed, and they are worth catching. The salmon shark's warm muscles, warm eyes, and warm brain operate at the speed that cold water would prevent in a fully ectothermic animal of the same size. It can process visual information faster, react more quickly, accelerate more powerfully, and sustain higher speeds for longer than any cold-bodied predator in its range. The endothermy is not a luxury. It is the fundamental competitive advantage that allows the salmon shark to hunt the prey it eats in the water it lives in. The short-fin mako, Isurus oxyrhynchus, is the fastest shark in the ocean, capable of sustained speeds of 35 kilometers per hour and bursts that researchers have estimated at up to 70 kilometers per hour, though the higher estimate remains disputed. It is a slender, powerfully built animal with a crescent-shaped tail of extraordinary hydrodynamic efficiency, a pointed snout, and large eyes that give it excellent vision in the dim light of the open pelagic zone where it spends most of its life. The mako hunts fast prey, tuna, swordfish, and other large pelagic fish that would outrun most predators with ease. To catch them, the mako needs to be faster, and it is faster, through a combination of the regional endothermy that the lamnid sharks share with the great white and the salmon shark, and a body plan that is among the most hydrodynamically optimized in the vertebrate world. The mako is not simply a fast shark. It is one of the fastest animals in the ocean, capable of competing with prey whose entire evolutionary history has been shaped by the need to be fast enough to escape predators. The mako's speed has made it a target for sport fishermen who prize it for the same quality that makes it extraordinary as a predator: its explosiveness on the hook, its tendency to leap clear of the water repeatedly when fighting the line, its refusal to be brought in without exhausting every reserve of speed and strength it possesses. The sport fishing pressure on mako populations, combined with bycatch in tuna and swordfish long lines, has reduced short-fin mako numbers substantially in the North Atlantic. In 2019, the species was listed on Appendix 2 of the Convention on International Trade in Endangered Species, the first pelagic shark species to receive international trade protection. The listing was opposed by several fishing nations, and the politics of it reflected the broader difficulty of conserving a species that moves through international waters, belongs to no one's exclusive economic zone, and is harvested by vessels from dozens of nations operating under different regulatory frameworks. The mako is a global animal in a world of national jurisdictions, And the gap between those two facts is one of the central challenges of shark conservation. The nurse shark, Gynglymostoma keratum, occupies a position in the popular imagination very different from the mako or the great white, and for good reason. It is large enough to be imposing, reaching 3 meters in length, but it is sluggish, spending much of its time resting on the seafloor in shallow tropical water, often in groups, sometimes piled on top of each other in a heap of spotted grey bodies that would be alarming if it were not so clearly unthreatening. The nurse shark is a bottom feeder, using its short, broad jaws to create suction and pull invertebrates and small fish from crevices in the reef. It has very different sensory emphases from the open water predators. The barbels near its nostrils, small whisker-like sensory organs, help it probe for buried prey. The small eyes reflect a lesser dependence on vision in the dim, complex environment of the reef bottom. The nurse shark is one of the most studied of all shark species in captivity because it tolerates captive conditions better than most, and it has been used extensively in research on shark learning and cognition. The results of that research have contributed substantially to the revision of the old picture of the shark as an unlearning, instinct-driven machine. The reef sharks, the grey reef shark, the white-tip reef shark, and the black-tip reef shark among them, are the sharks that most recreational divers and snorkelers encounter, and they are the species whose behavior most clearly illustrates the complexity of the shark's social and cognitive life. The grey reef shark, Carchahinus amblyrhynchos, is a medium-sized species of the Indo-Pacific reefs, and it has one of the most clearly documented threat display behaviors of any shark species. When a grey reef shark feels threatened, it performs a ritualized display. It arches its back, drops its pectoral fins, raises its snout, and begins an exaggerated lateral undulation of the whole body, the movements becoming more pronounced as the threat is perceived to increase. This display is a communication directed at the threat, and it means something specific. I am feeling cornered. I'm about to defend myself. Back away now or face the consequences. Divers who have learned to recognize and respect this display avoid being bitten. Divers who have not learned it, or who have ignored it, have been bitten. The shark is not attacking randomly. It is communicating in the only language available to it, a clearly legible social signal to a creature that it perceives as a threat in its territory. The bite, when it comes, is not predation. It is a defense response delivered after a warning that was either not understood or not heeded. The silky shark, Carchahinus falciformis, is a sleek, fast-moving species of the open ocean, one of the most abundant large sharks in the world, and one of the most heavily fished. It is found aggregating in numbers around fish aggregating devices, the floating structures that commercial fishing operations deploy to concentrate tuna. And this aggregating behavior, combined with the silky shark's willingness to approach these structures, makes it extremely vulnerable to bycatch. Observers on tuna longliners in the Pacific have counted hundreds of silky sharks in a single set. In the purse, seine fisheries that encircle schools of tuna, silky sharks are caught by the thousands. The silky shark population of the Indo-Pacific has declined dramatically in the past few decades, and it is now listed as vulnerable on the IUCN Red List. The silky shark is not a famous species. It does not appear in films or in nightmares. It does not carry the cultural weight that the great white carries, but it is one of the most important pelagic predators in the tropical ocean, and its decline is one of the quieter parts of the broader story of what is happening to the sharks. The night is when the reef sharks move. During the day, the white-tip reef shark rests in groups on the bottom of shallow reef channels, its body perfectly still, its gills pumping water across them in the slow rhythm of a resting animal. But as the light fades and the reef darkens, the white-tip reef sharks rise from the bottom and spread out across the reef in hunting groups, moving through the complex three-dimensional architecture of the coral in a coordinated sweep that drives fish out of crevices and into the open water where they can be caught. The hunting is social. Multiple sharks work the same section of reef simultaneously, each responding to the movements and reactions of the others, each benefiting from the disturbance that the others create. It is not cooperation in the deliberate, planned sense that wolves cooperate, but it is a shared activity with shared benefits, and the sharks that participate in it catch more fish than a shark hunting the same reef alone would catch. The white-tip reef shark at rest is one animal. The white-tip reef shark hunting at night in a group is something more complex, something that the word instinct does not fully account for. The night reef is a different world from the day reef, and the sharks that move through it at night are moving through a world that their prey cannot see clearly in. The fish that hide in the reef during the day have retreated into the coral at dusk, tucking themselves into crevices and under ledges, relying on the complex structure of the reef to keep them safe from predators that hunt by sight in the daylight. But the white-tip reef shark is not hunting by sight in the darkness. It is hunting by the lateral line system that detects the pressure waves of movement, by the electroreceptors that detect the bioelectric fields of the fish pressed against the coral, by the chemical gradients that carry the scent of the fish in the slow night current. The shelter that the reef provides from visual predators provides no shelter from these senses. The fish hidden in the crevice is visible to the shark through the electric field it generates, visible through the pressure waves of its breathing against the coral wall, visible through the chemistry of its body in the water. The reef is not hiding the fish from the shark. It is simply making the fish harder to extract once found, and the white-tip reef shark has learned to work that problem, to follow the signal to the source and force the fish from its shelter into the open water where the jaws can find it. Let the image of the reef at night settle in your mind for a moment. The coral is dark, its colors invisible without light, its structure a landscape of shadow and deeper shadow. The fish are pressed into the crevices, their bodies still, their metabolisms slowed for the night. And through this landscape, the white-tip reef sharks are moving, their lateral lines reading the wall of the reef, their electroreceptors scanning the coral face, their bodies weaving through the complex architecture of the reef, with a familiarity that only comes from having made this passage, or a very similar passage, every night for years. The shark knows this reef the way you know the layout of your own home in the dark, not because it can see it, but because it has moved through it so many times that the knowledge is in the body. The deep-sea sharks have their own night, which is not bounded by the cycle of the sun because the sun does not reach them. Below 1,000 meters in the bathypelagic zone, it is always night, always cold, always dark. And in this permanent night, the sharks that live there have adapted to the specific challenges of finding prey in conditions of complete darkness and extreme pressure. The prickly dogfish, Oxynotus brunniensis, is a small, stout, deep-sea shark with rough skin and a pair of large dorsal fins. The velvet belly lantern shark, Etmoptera spinax, is bioluminescent, producing light from photophores on its underside in a pattern that may serve as counter-illumination or as a species recognition signal in the dark. The Portuguese dogfish, Centrosymnus coilolepis, is found at depths of more than 3,000 meters, making it one of the deepest dwelling sharks known, and it produces a liver oil rich in squalene, a compound that provides buoyancy at depth in an animal that lacks a swim bladder. The deep-sea sharks are not the glamorous predators of the open ocean and the coastal reef. They are the quiet, slow, cold inhabitants of the darkest and most extreme part of the shark's already extraordinary range. The relationship between the shark and the human being is as old as the human relationship with the ocean, and it has always been complicated by the fact that the shark is not afraid of us. Most of the animals that have shaped human experience of the natural world, the lion, the bear, the wolf, are animals that we can, under the right circumstances, frighten. They have learned to associate our presence with danger. They retreat from us. The shark has not learned this, not because it is stupid or incapable of learning, but because for most of the history of that relationship, we were not dangerous to the shark in the water. We are terrestrial primates who entered the ocean recently without the adaptations that would make us effective predators in that environment. The shark, encountering a human swimmer, has no evolutionary reason to treat that encounter as a threat. We did not shape the shark's evolutionary history the way the shark shaped ours. The fear runs in only one direction, and that asymmetry is part of what makes the encounter between a human being and a large shark in the water so profound. We bring our fear with us. The shark brings its curiosity, its sensory investigation, its ancient pattern of encountering the unfamiliar in its environment and finding out what it is. The photographers and scientists who have spent decades in the water with sharks describe almost uniformly a different animal from the one that popular culture has created. Not a harmless animal, not a safe animal, but a complex, curious, behaviorally sophisticated animal that is, in most circumstances, conducting an investigation rather than an attack, gathering information rather than pursuing prey, responding to the environment with the full repertoire of a sensory system and a behavioral flexibility that 450 million years of evolution has built into it. The diver who enters the water calmly, who moves in a way that does not mimic the behavior of prey, who observes the shark's behavior and responds appropriately to its signals, typically has a different experience of the shark than the popular image would predict. Not always, not in every circumstance, but typically. The ocean does not belong to us, and the sharks that have been in it for 450 million years were not placed there to threaten us. They were placed there, or more accurately, they evolved there, to be what they are: the apex predators of the marine ecosystem, the animals that regulate from the top everything below them, the creatures that the entire ecosystem of the ocean has been organized around for longer than any other predator lineage in the history of animal life. Their presence in the ocean is not a problem to be managed. It is a fact of the ocean's biology, as fundamental as the chemistry of the water or the movement of the currents, as old as the continental shelves they swim over, as essential to the ocean's continued function as anything else in the system. Let your breathing settle now into the slowest rhythm it can find. The shark is in the water right now, as it is every night, as it has been every night for 450 million years. The great white is somewhere off a rocky coast, its warm-cored body moving through cold water with the efficiency that hundreds of millions of years of selection for exactly this purpose has produced. The whale shark is filtering the open ocean, somewhere far from any shore. The Greenland shark is in the Arctic, moving at its single kilometer per hour through water it has been in for hundreds of years, patient beyond any definition of patience that the surface world has produced. The hammerhead is over the sandy flat, its wide head sweeping back and forth, reading the electrical landscape below it. The blue shark is crossing an ocean. The silky shark is somewhere near a fish aggregating device in the tropical Pacific. The white-tip reef shark has risen from its resting place on the bottom of the reef channel and is moving through the dark coral, reading the reef with its lateral line and its electroreceptors, hunting in the way it has hunted every night of its life, and in the way its ancestors hunted every night of their lives back through the generations, to a point in time when the coral reef itself did not yet exist in anything like its current form. All of this is happening right now. The ocean is full of it. The vast, dark, moving, chemically complex, electrically active, pressure-stratified ocean is full of sharks doing what sharks do, and has been full of sharks doing what sharks do since before anything on land was complex enough to imagine it. You are not in the ocean. You are warm and still and breathing the air of wherever you are, and the ocean is somewhere else, doing what the ocean does. But for this hour, or for the part of this hour that remains before sleep takes you, the ocean and its sharks are part of the space you are in. The dark water and the moving shapes and the 450 million years of presence and the seven senses and the electric fields and the pressure waves and the bioluminescence of the cookie cutter in the twilight zone and the single kilometer per hour of the Greenland shark in the cold Arctic dark, all of it is here, in the room, in the dark, in the quiet. The sharks do not need to be here for you to feel that. They are where they are, doing what they do, as they have always been doing it. But the knowledge of them, the weight of what they are and what they represent, and how long they have been in the ocean, that weight is available to you right now, and it is a different kind of weight from the weight of anxiety or urgency, or the thousand things that the day deposits in the body and the mind. It is the weight of deep time, of something that has been patient for so long that patience is no longer a word that captures it, of something that fits its world so completely that the fitting is invisible, that you only see it when you look for it, when you slow down enough to recognize that the shape moving through the dark water is not a threat and not a monster, but simply one of the oldest things alive on this planet, going about its ancient business in the dark. Sleep now. The sharks are in the ocean. The ocean is where it has always been. Everything is very deep and very patient and very old, and the night is as long as it needs to be, and the water is moving in the way that water moves, and the shapes are moving through the water in the way that the shapes have always moved. Sleep. The ocean holds them. The dark holds everything. You are held, too, by whatever holds you, in the warm, safe dark of wherever you are, and the 450 million years of the shark's presence in the world is not a threat to you, but a companion, a piece of knowledge about the depth of the world that can make the night feel larger, and the morning feel, when it comes, like something worth waking into. The great white is in the cold water, the whale shark is in the open ocean, the Greenland shark is in the Arctic dark, the hammerhead is reading the sand, the blue shark is crossing the water between continents, and the ocean is full, as it has always been full, of shapes that have been in it since before the first tree and the first flower and the first breath of air taken on land by anything at all. Very old, very patient, very still in the deep, very alive. Sleep. The sand tiger shark, Carcharias taurus, is one of the most visually striking sharks that divers encounter in shallow coastal waters, and it carries one of the most dramatic behavioral adaptations of any shark species. Sand tigers are large, reaching 3 meters, with long protruding teeth that make them look formidable even when their mouths are nominally closed. But the behavioral adaptation that makes them genuinely remarkable is their practice of gulping air at the surface. The sand tiger swims to the surface, opens its mouth above the waterline, takes in air, and swallows it into the stomach. This trapped air provides buoyancy, allowing the sand tiger to hover motionless in the water column without expending energy on swimming. The sand tiger uses its stomach as a swim bladder, a function that most sharks compensate for through the oil in a large liver. The sand tiger has found a behavioral solution to a physiological problem, managing its buoyancy through conscious behavior rather than passive physiology. It is one of the clearest examples of the shark solving a problem in real time, adapting behavior to meet a specific need in a specific moment. The lemon shark, Negaprion brevirostris, has been the subject of more long-term behavioral research than almost any other shark species, because it is accessible in shallow tropical water, tolerates observation, and returns year after year to the same nursery areas where it was born. Studies of lemon sharks at Bimini in the Bahamas have followed individual animals across decades, using natural markings and genetic identification to track individuals across years and generations. What these long-term studies have revealed is one of the most detailed pictures of shark social life available for any species. Lemon sharks form long-term associations with familiar individuals. They prefer the company of familiar conspecifics over unfamiliar ones. They learn the layout of their home range and navigate it efficiently, and they show a capacity for social learning, observing the behavior of other sharks and modifying their own behavior in response to what they observe. The lemon shark is the shark that has done the most to revise the picture of the shark as a solitary, non-cognitive animal. The research on it suggests instead an animal with a working memory, individual recognition, and the kind of social bonds that we more readily associate with mammals. The basking shark, Cettorhinus maximus, the second largest fish in the ocean, is a filter feeder that aggregates seasonally in surface waters, where plankton blooms are dense. In spring off the coasts of Scotland, Ireland, and Cornwall, basking sharks gather in numbers that have occasionally reached the hundreds in a single bay, their enormous dorsal fins cutting the surface as they cruise back and forth. They move in loose formations, sometimes following each other in long chains, behavior that may be related to mating. The basking shark's aggregations represent one of the most dramatic wildlife spectacles in the temperate ocean, and they also represent a gathering of cognitive and social complexity that the shark's reputation consistently fails to predict. The ocean at night is not sleeping. The biological activity of the ocean is as intense at night as during the day. The Deal vertical migration brings hundreds of millions of organisms from the deep to the surface under the cover of darkness. The reef sharks that rested during the day are hunting. The pelagic sharks that were cruising the surface layer during the day may descend to cooler water or may continue cruising, their 7 senses reading the dark ocean in the same way they read it during the light. The shark is in the night ocean, as it is in the day ocean. continuous and patient and doing what it has always done. The weight of 450 million years, held quietly in the dark of wherever you are, is not a frightening weight, it is a grounding weight. The knowledge that there is something in the world that has been doing what it does for 450 million years, that has survived everything. That fits its world so completely that the fitting is invisible. That is in the water right now, doing what it has always done. That is as patient as rock and as old as the sea. The shark is in the ocean, and the ocean is where it always is, and the night is doing what the night does, and everything is as it is. Let your body be heavy and your breathing be slow, and the darkness be comfortable, and the knowledge of the sharks in the dark water be the last thing your mind holds before it lets go of holding things and allows the night to do what the night does, which is to carry you slowly and without effort from where you are to where you are going. The same direction the Greenland shark is going at 1 kilometer per hour through the cold Arctic dark. Not somewhere specific, simply forward, simply through, simply continuing in the direction that 450 million years have established as the direction. The ocean is very deep and very dark and very full of things that have been there for a very long time. You are not in the ocean, but the ocean is part of the world you are in, and the sharks are part of the ocean, and the 450 million years they represent is part of the night, and the night is where you are, and where you are is held. The way the ocean holds the shark, the way the dark holds everything, without effort and without end. Sleep. The sharks are where they have always been. The ocean holds them. The night holds everything. And you are held too, warmly and completely, in the quiet dark of wherever you are. Sleep.